Okay, so our lecture today is going to cover the growth of dinosaurs, or ontogeny. And the important thing about ontogeny, of course, is it gives us lots of information about these animals, right? Growth is really important for understanding how animals actually live, life histories as well. If we get done with this early, I'm not going to release you because I will use more. Every minute I save, I will use for the last lecture's topic, which will be extinction events. So the more time I can give to that, the better. Because I think we're gonna easily run over time on that. So I'm gonna try to use up as much of today's time for this, but I'll also, if we get done, like I said, we'll move to the next lecture topic. What you're looking at in the picture is from a recently published paper. On the left are juveniles of the animals, and then on the right are the adults. And one of the things to note here is this is the primitive condition for the Archosaurus with a juvenile. And this is common in many animals, very, very large eye relative to the rest of the head, a relatively large brain compared to the rest of the head, right? The brain space is actually much, much higher. Relatively narrow snouts in these guys compared to the adult stage. And they have what looks like a more teardrop shaped head in that way. Adults, at least for the crocodilians, are very, very elongated, and they also have much smaller brains. So the brain does not grow nearly as fast as the rest of the head. And of course, the eyes also do not do that as well. What you see in dinosaurs is that they tend, at least in the theropods that lead to birds, they tend to be more and more juvenile in their appearance. Right, here's a velociraptor. What you can see is you have that very characteristic juvenile stage, right? Very similar to what you saw in the crocodile. The adult retains a very crocodilian-like head in the sense that the proportions grew in some of the same ways that you saw in the crocodile, but there is a larger eye, so it's retaining that slightly larger eye. And then as you come down here into things that are more and more similar to birds, right, in things like Archaeopteryx, you see that they look more and more like the juvenile stage. They retain this very large head and therefore brain for body mass, and they retain this very large eye, and they have a relatively narrow snout in that way. So how fast do dinosaurs grow? We've talked actually about this in a number of different ways. I've mentioned it at least on every single group that we talked about because that's sort of a question of interest. We're going to look today at a couple of different papers, so there are papers posted on Blackboard for you guys to read. But there is also, we're going to look at this through phylogeny. So we're going to look at this in the realm of family trees, right, and see how growth rates may have changed with different groups and how they may have changed through evolutionary time. Bird growth, that's why I pulled up Google for us. Take a quick look at bird growth. Here's my mouse. So bird growth is very, very different than what we think of as classic reptilian growth. It's very, very fast, right? A month is a very short period of time for that animal to grow. That's part of the reason we grow chickens, right? They grow really nice and fast. It's determinate. They reach a very finite size and they cease growth immediately. So they reach some size, that's the adult size, and then they're done growing. So they shunt all of the rest of the resources into maintaining and then also reproduction, should they survive. And then, of course, the birds don't you don't have chicks reproducing, right? The chicks are specialists at growing. You don't have reproduction until you reach the final adult size. That's fairly different from what we think of as a classic reptilian mode of growth, which it tends to be relatively slow, often seasonal, so when food is available. It is indeterminate, although not entirely, but it is indeterminate in the sense the animal will continue to grow throughout its life by and large. And sexual maturity usually occurs below the largest size, so sexual maturity is reached below the largest size possible. Now, we did already talk about this in dinosaurs, and I warned you that dinosaurs sit in an intermediate position between what we think of as classic reptiles and what we think of as very, very advanced reptiles in the form of birds. And so you would expect them to have a broad range of strategies that would straddle this in this. So the age of dinosaurs is defined by the use of what are called lags, which are lines of arrested growth. The image to the right is a picture of a cross-section bone, and these are very difficult actually to see, but these black lines are what are called the lags. And that should give you some idea, one, about the difficulty of identifying lags, and two, some information about the skill it takes to sit down and really look at bones over and over again and find them, right? So we need to be careful when we look for them, and we need a real specialist to go through it. But lags are developed in the same way that tree bands are developed, right? So the tree is growing very, very rapidly. The bone grows rapidly in the same way. during the growing season, or if it's a wet season, then a wet season, right? There's a lot of growth. And then come the winter or come the dry season, that will result in the bone growth slowing down considerably, and the lag will build up at that point, which is a period at which the bone is not growing very slowly, so the bone is very, very dense at that area. And then again, when the year resumes the following year, the growth continues and the bone becomes more spaced out, it's less dense, and you see that as that white line. These are really, really useful in that way because you can count them. These are not great ones to count, but there are some that are very easy to count. These are some very, very distinctly obvious ones here. Now the lighting is different, so of course you're welcome to use different lighting, and we do this regularly as well as we shine light in different patterns and in different ways to try to get a better image. What you can see here is that these bands are very, very clear. The picture below that panel B is actually one where they were taking alligators and growing them for no numbers of years. So alligators are raised in farms, not for meat, but for their skin. The meat is used then as food, but the meat is the skin is what people primarily are concerned with. And so when they were growing these animals, they expose them to fluorine, and that stains the bone, and that's that ring. And they were confirming that lags are built up every year, right, with the similar archosaur. So they could confirm that lags should in fact be yearly bands. Right. There was a lot of debate when this first came out. Are lags yearly? Are they bi-yearly? Are they laid down randomly? Are they just laid down whenever the animal starts to slow in growth? And by and large, they appear to be yearly, so we can use them.
How did they figure it out that it was yearly, not like bi-yearly?
With stuff like this, so growing lots and lots of alligators, having stained the bone at one known time. So you'd come in, your master's project would be, you would arrive, pour in some fluorine in with these alligators, come back a year later, collect when they were done collecting alligators, get the long bones from them, and then you would section them and count the rings, right? And you should have very distinctly a ring between two lags. And if that ever is not the case, right, then that would immediately throw into question whether lags were yearly or not. And then this down here, of course, is another individual. And what you can see, of course, as you expect, dinosaurs have leans towards indeterminate growth, of course, is that the first, let's say, teen years or younger, the animal's growing very, very rapidly and putting on lots of weight, and so the lags are well separated from each other. Of course, as you get up to a larger and larger and larger size, those lags will stack up on each other because the animal is not growing nearly as fast. That doesn't mean that they're not there. You can actually count them here. But what you realize is that it gets harder to do that, and you need a really good cut in the bone to do that. So this is all relatively new. Like I said, this isn't particularly old information in the sense that lags have been used now in your lifetime for most of it, but this is relatively new to the paleontological field. And why is that the case?
Because they didn't want to cut open bones.
They didn't want to cut open bones. So there's a really strong incentive in paleontology to protect what you have, right? You don't get very many. We've talked about T-Rexes. You really get a handful of bones. In fact, we could store all of the Earth's known T-Rex specimens in this room. Now we have to pack them in there carefully. We could store them in here in this room. And so if you have only that many bones, you act very cautiously about cutting them with bandsaws. Right? That doesn't seem like an attractive option. But that is what people started to do, and in fact part of this is what happened when Sioux was being excavated. They had to cut the pelvis in half to remove it, and by doing so they cut other bone elements. And they brought them back to the lab. They were actually able to look inside them, and that part of that was the inspiration for spending more and more time doing it. Jack Horner, who was doing a lot of the excavation, was also doing that. Remember, he was doing a lot of work with myosaurs, and they had lots and lots of myosaur bones. And one of the things he was very interested in doing is saying, well, what if we start to look inside the bones? Do we see the microscopic structures that we expected to find, right? And if you remember back in some of those lectures, you saw a video where him showing you the inside of those bones. So he, by and large, was very happy to cut bones. But he had to convince the community that, yes, it's worthwhile. There is a cost to doing it. Of course, it does damage the bone, and you lose elements of the bone, right? The saw removes a piece of it, but it also erodes around that piece. So you do lose a little bit of that bone in the final process. So this is a paper from 2001, and 2001 was the first paper that examined growth of dinosaurs across a broad range, so across the phylogeny in that way. Prior to this, growth had been examined sporadically, but in just a few members, which is fine and useful to that. but it doesn't give you a very strong indication of how dinosaurs as a group grew, right? It gives you an indication of how individual species grew. And this paper said, well, that is a weakness. What we will try to accommodate now, and what we have the power to do, is to say, well, let's bracket the entire phylogeny. Let's take primitive end members and very advanced end members and compare them and see what it looks like. Are all of them growing the same way? Do we see what we would probably expect to see, which is sort of a gradation of growth, right, as we get from these more primitive groups to these later groups? Or do we see sort of a spattering of different things as we go out? These are the members that they selected. I'm just confirming to you that the ornithischians and the saurischians, of course, are included within this. There's some very advanced members like Myosaurus. There are less advanced members, at least within the ornithischians. There are very, very few ornithischians at the time that we could examine. Psittacosaurus, which you've also looked at, is primitive ceratopsian, right? Still a relatively advanced member within that group, but a very primitive ceratopsian. Within the saurischians, of course, which again, people are very interested in for a variety of reasons, we have a number of different things. We have a very, very primitive sauropodomorpha, right? So we have a prosauropod, and then we have what we call a true sauropod in this way. I just want you to know that these outlines, these black outlines that they chose, are much old. They look very outdated now relative to what we think of, but that's fine. And then within the theropods, which people spend, I would say, the majority of the work on, there are some members in here. Shuvia, this guy you won't know. We've never looked at him, but this animal, Syntarsis, is a relatively primitive theropod, and that will provide information. And then, of course, they examine Archaeopteryx. And you actually have already seen the Archaeopteryx growth curve, but we're going to compare it here to the other members. So these are the growth curves that they developed. And the way you go about doing this is you need at least a few specimens of each animal, and you need it at different time periods. So preferably you have specimens that would suggest that they're different ages old by different sizes, right? You won't know until you crack the bones, but the best place to start cracking bones is where you say, well, we have a range of sizes, so I want some small ones, I want some medium-sized ones, and I want some large animals within that. And so what you can see here, one, of course, the growth is very similar to what we see in modern animals. It's sigmoidal. You have a relatively slow period initially where the animal is just packing on a little bit of weight, a little bit of weight, a little bit of weight. Then it enters an exponential growth period where it grows very, very rapidly, and then it starts to tail off, and it enters into a decay area, at which point it's roughly the final size that will be. It may grow a little bit, but it will not increase in size drastically beyond that. And it's during this growth period that we often consider animals juvenile, or that we expect to find juvenile animals, because growth is very, very expensive, and so they can't contribute large amounts to reproduction at that time, right, if you're growing exponentially. So what they found, let's start with the ornithischians, which unfortunately, I don't know why they did this, but they split them up across from each other. And unfortunately, my bar down here is covering up my age. But what you can see for this guy, Myosaurus, is Myosaurus would remain relatively small until maybe about 4 years old. So not that these animals are teeny tiny, but that these animals are small relative to the adult, and they haven't begun to grow exponentially. However, between the years of 4 and 6, these animals are going to basically pack on all of their weight. So they're going to go from being relatively small, maybe up to your waist height, to being animals much, much larger than a human in about 2 years. And so that is phenomenally fast growth, and it is very, very difficult to achieve in the sense that you have to have a lot of resources available, and you have to have, probably, and we expect this as well, have to have some sort of endothermic capability, because you have to be working all the time to move material through the body, right? And they need to be really active to do that. Keep in mind as well that we mentioned that dinosaurs are probably breeding before they're fully adult, although in Myosaurus, this animal has such a short exponential growth period that may in fact mean that the animal doesn't really have a chance to breed, right? It would only have 1 or 2 seasons in which it's growing exponentially before it would enter into the adult stage and breed. If you look at the Psittacosaurus, you see an animal that is fairly different. So the Myosaurs are beginning their exponential growth at 4 years old. And the Psittacosaurus, which is a much smaller animal, right, maximum size, not much bigger than my waist height. These are not huge animals. They don't begin exponential growth until about 5 years old, and they don't reach the end of that exponential growth period until about 10 years old, right? So they're spending 5 years of growth. That's much, much slower in that way. They're attaining a much, much smaller maximum size, and you would expect in that case that yes, in fact, animals are probably breeding during that time, right? So these animals are doing something very, very differently. So that would also suggest to you, and not unexpectedly, that the ornithischians are probably doing different things within their own group, right? Probably animals that are more primitive will behave much more like this, with relatively long exponential growth periods, followed by breeding throughout that time frame, right? That they're going to have to, because the adult animals, you can see here the oldest known animal is about 10 years old. That suggests that a lot of these animals aren't making it to that maximum size. Most of them are going to be consumed before they reach that leveling off point. If you look at, so that's the ornithischians. Like I said, they're relatively scanty on those. If you move forward to the sauropods, there's a couple of things here. One, we're going to talk about this more completely as we move through the lecture, but this is a fairly primitive, you can think of this in the same order as, it's a more advanced plateosaur in that sense. So we think of plateosaurs as really good examples of those prosauropods, right? And this particular Massa spondylus is also relatively close in that way, this sort of biped, quadruped intermediate, where they are sitting now, they have some of the elements that we think of as really good sauropods, but they have a lot of the elements where you think of as just these classic bipedal theropod-like dinosaurs at the same time. And these guys, you can see how long it takes them. They are starting their exponential growth actually a little bit earlier than 5 years, so let's say around 5, and then ending that relatively late in their lifespan, maybe into the 15s or even into the 20s. This is a really long period of growth. And so growth is very, very slow for these guys relative to what we think of as sort of our fastest growing dinosaurs. And so you can imagine, as a result of that, that there are that the things that we often assume about birds, things like determinate growth, being very warm-blooded in that way, and being these really active growing animals, are certainly not present in these early groups, right? That doesn't seem to be characteristic of these groups. These appear to be more from ancestors that had these slower growing elements to them. If you look at, by the time you get to an apatosaur, of course apatosaurs represent what we think of as a very classic sauropod in that way, sort of the middle of the road sauropod, fully quadrupedal, really big, huge necks, big long tails, big bulky animals, tiny little brains, right? These are the sauropods that people think of. These are the sauropods people draw. You see it's a little bit different. Exponential growth is still starting at about 5, but then ends well before 15, probably around the 10-year mark. And that means that to get to that size, right, these animals are going, again, from a relatively small animal to a fully adult animal in the course of just 5 to 10 years. Very, very rapid growth. That means that if you came back to an animal every year, it would be that much larger, right? It wouldn't just be a little bit bigger. It would be enormously larger every time you looked at it until it reached into those teen years. Now this, again, we actually have some questions about whether sauropod growth is as fast, but it suggests in any case that sauropods are still within the realm of similar dinosaurs, and that these are not animals that live hugely long. They may be very large, but they don't live hundreds of years. These are still animals following the classic example of a relatively short lifespan, lots of eggs, huge mortality, couple of adults. Right? That seems to be true for dinosaurs. Okay, so the sauropods appear to do a couple of things. They appear to get bigger faster, and they appear to truncate that exponential growth, which makes sense, right? You're really vulnerable, and so you can get high up on that exponential growth phase, and you want to get through it relatively quickly. Now, of course, the cost of that is that you have to be able to find food, but in any case, let's look at the theropods now. And again, I apologize that the way that the graph is set up, I just pulled it out of the paper. So, but this is a let's look at this guy first. This is a relatively primitive theropod. It's not a huge animal, and you can see that it begins exponential growth at 2 and probably ends it at about 5. You can see that members live well beyond that exponential growth period, and in fact, the fact that there are dots below and dots above may, in fact, it's very hard to tell with the number of specimens we have, but you can anticipate that may be a male-female difference, right? If you have dots that appear above and dots that appear below a line, and the line sits right between them, you're getting an average, but that probably means there are sexual differences, and you should anticipate that would be the case for these guys as well. But these guys are growing. They're growing at about 9 kilograms per year, which is not a huge amount in the sense it's fast, but it's not as fast as you can see in later members. This is a later member. It grows even slower, but it lives for only a couple of years in that way. And we already talked about Archaeopteryx. We said that by the age of 3 or 4, these animals are basically done growing. And so that, in that way, is pushing what this is classic theropod growth curve, is pushing it backwards, and it can't go back to 0, and so it's reaching a wall, and as a result, it has to curve up faster to get to that exponential growth. And that's effectively what birds have done. They've pushed it so far backwards that it almost looks like a line once you get on it, right? You're very, very small when you start out, and then you just go straight up the wall, and then you level out immediately, right? So it is hugely truncated in that way. So birds are very different. They've managed to push that all the way back up, probably up into the limits of almost how fast a wild animal can grow, right? You just usually can't get access to food that frequently. So how fast do dinosaurs grow, and where do they sit? Well, they span the whole range. They go from what we think of as reptile. This very dark line is the dinosaurs. They go from what we classically think as something like a reptile, all the way up into what we think of as precocial birds, not the altricial birds, but the precocial birds and eutherian mammals in that way. So they certainly across that entire gap. And again, that is not unsurprising for what we've covered so far. They really do appear to be this very intermediate group in that way. They're intermediate between more primitive early members and very, very advanced members that we see alive today. Okay, so that is the dinosaur growth curve from 2001. That paper is very interesting, relatively easy to read. You will, if you look it up, you will see that there are a number of errata associated with it, which means that there were problems with the paper when it was first published. Those turned out to be minor in the sense that some of those points on that paper were slightly off, but they're off by so little that even when I projected them on the screen, you wouldn't be able to see the difference with your eye. It changes the equation associated with them, so you would have to know that for back calculation stuff, which was important for future work, but for visual presentation it was unaltered, so I didn't change any of that material. But if you're going to cite it in your own work, you would want the updated potential with that. When we look at Tyrannosaurus, and I think this is one, of course, that we've looked at many, many times, partially because they're very, very cool, partially because people have really looked at these very closely, and that's also because they're very cool. But one of the things people have certainly asked about Tyrannosaurus is, why is Tyrannosaurus so large? Why does it get so big, right? Are all members like it, or are members very, very different from Tyrannosaurus in that way? This is a nice, I just like this guy. I don't know why this Tyrannosaurus arms are so beefy, or why it looks like it's sort of cuddling a pumpkin, but it does have its arms in sort of a weird, it's like a football almost. It's trying to, but anyway, it's eating the ceratopsian, which apparently did not make it. So this came out after that other paper, right? So there was no Tyrannosaurus growth curve in the other paper because we didn't have enough Tyrannosaurus skeletons at the time. And they were able to look at Tyrannosaurus, but actually Tyrannosauridae, the group, they were really able to look at that group as a whole. And so that is one of the more interesting things. Again, when dinosaur growth was first examined, you could examine it at a species-by-species level. Today, we actually have a number of species that have been examined, and so if you want to be published, we need to examine it in the higher-end journals. You need to examine it in a broader understanding so that we can understand how it fits in relative to everybody else, right? So you need to present a bigger picture that way, and that's how science proceeds. We had to wait till we had enough skeletons, and we also had to wait until we had enough ages, right? It doesn't help if every Tyrannosaur that you've ever collected is 3 years old. You have no idea how fast they grow. 3-year-olds are this big. Okay, we get a very good understanding of how old 3-year-olds are. We don't know how fast they get there. And then they also, at this point, had a lot of close relatives of Tyrannosaurs. So within that, like I mentioned, that Tyrannosauridae. So I will not lie to you. This, of course, is from Wikipedia, but I just wanted to let you know how Tyrannosaurs as a whole are related to each other. And the only thing I wanted you to take away from this is there's some debate about whether there's another group within the Tyrannosauridae, so whether we should split them into 2 groups, with the Albertosaurs in one branch and the Tyrannosaurs in another branch, and then actually call them different names, or should we, for the moment, just split them out and wait to call this other branch something? And so it's sort of this is an academic discussion at this point, so we don't need to worry about it. But I just wanted you to be aware. And actually, one of the interesting things is Tyrannosaurus does fall out as a fairly what we could derived member, right? It is far down on the tree, but there are actually other members that are probably more derived than it, right? That appear. So it's actually not the most derived Tyrannosaur that ever walked on the earth. And this is what they found. They found that, okay, so here are other Tyrannosauridae. These, again, Albertosaurus is probably the most primitive member of that group, and these are some other members. You may or may not know these names. It's not terribly important. What they found was that the exponential growth period, okay, it all starts at about, again, about 5 years old for these animals, and they all end the exponential growth probably on the order of about 17 years old. Exponential growth has ceased at this point. The difference between these growth curves, though, is very, very important. Where these guys are all growing at about the same rate, the slopes are all about similar, right? Tyrannosaurs evolved the way in which they would push that slope way up. So again, they're doing that thing that I talked about with the birds, but they're also doing something else. I'm sorry, they're not doing that thing that I talked about with the birds, where the birds are pushing the slope backwards up against the wall. They're actually physically lifting the maximum size, right? And by doing that, the curve has to come up much, much faster. So you have two options. You can either drag the curve out to accommodate that maximum size, which these guys did not appear to do, or you can retain the maximum size reaching potential at the same time, but that means you have to extend the curve up much faster in that way, right? You can't get to this point going at this rate. You have to come up faster to get up to that point if that's where you want to meet, if you start elsewhere. The other thing about this, and again, I'm going to warn you about this just because I want you to be thinking about it, doesn't mean it is true. Notice here that we have points that bracket each side of this line. Again, that should give you some idea that, well, either we're getting good estimates around this point, or there might in fact be two lines. There may be a male line and a female. Females would probably tend to be larger in that way. So just keep that in mind, because we don't know per se, but when you see that in the future, just be thinking about that. What if we had more specimens? Could we try to find something out like that? But Tyrannosaurs and all of these other members grow the same amount of time. That exponential growth is the same, but the speed of Tyrannosaurus is so fast relative to that. You can see here that a Tyrannosaurus is putting on almost 800 kilograms per year at that exponential growth stage. These other members are putting on about 100 to 115. So it is taking that and multiplying that by 6, 7, or 8 times what other members are doing. So it is growing much, much faster in that way, right? And that also suggests to you, one, that there's a lot of prey base, because to grow that fast, you're going to need a lot of food. And two, that these guys are getting eaten a lot. Like the smaller theropods, they really have to be careful, because that thing's getting big quick.
I think Tyrannosaurus is the only species that is hypothesized that it was a scavenger, right?
So Tyrannosaurs we've talked about. Certainly Tyrannosaurs did scavenge. There's almost no way Tyrannosaurs wouldn't have scavenged. It's unimaginable. But they are also, there's a lot of good reasons to think that it's also hunting as well. But it doesn't mean that it wasn't a scavenger. And certainly it would have been a very good scavenger.
Because I cannot assume that you can attain such a growth without scavenging, right?
Right. Whenever you find a body, that's great news for you. You get right into that moldy corpse and you take out as much meat as you can. But you can't rely on that to sustain this kind of growth. You're going to need something else. So if you look at that, so how fast is 800 kilograms or the 767 kilograms per year? That puts you at about 2 kilograms per day, which is pretty fast if you're thinking about that, right? That's a noticeable difference day to day, right, of putting along a lot of weight. So that's about 5 pounds per day. If you put on 5 pounds per day, you would be very unhappy. If you imagine, let's say that Tyrannosaurs are converting their food to body mass at about 50%. So for every 2 pounds of food, they get to put on 1 pound of body mass. That would be very generous for them. Then you need about 9 pounds of food a day, right? Somewhere in that realm to supply that much growth. And then that would mean that you need on the order of about 250 to 300 pounds of food, right? So an adult, some large number of small animals, or maybe one moderately sized animal. You would need about over a ton and a half of food a year, right, to compensate for that. And that's at very, very, very high conversion ratios. So that conversion ratio starts to fall. You start to need a lot more food, right? So you can imagine these animals are, one, eating all the time, and two, they're hungry all the time, right? So you don't want to be around them, and they're aggressively hunting you down. And that seems to make good sense, and that would be in line with what we expect for a smaller tyrannosaur. Maybe at some point they can stop eating so much, but they do need to eat a lot to grow that fast. Max age for Tyrannosaurus, from what we saw in that, is about 30. We don't have any animals that are over 30, so this again is that live fast, die hard, and it is not dissimilar from what you saw in all the other dinosaurs we've looked at so far, right? 30 would be a very old animal. We found animals that don't live to more than 5, but we don't find a lot of dinosaurs that live more than 30. Right? So 30 is a pretty old dinosaur usually. Sexual maturity is probably reached actually during that exponential growth. That doesn't mean that their output is very high, but it means that they do get to start getting output into the world, right? They do get to start to generate offspring. And then, of course, there's a huge advantage for these animals. Once they escape that exponential growth curve, they can start to generate enormous amounts of offspring because all of that energy that they would have taken and used for growth can now be dumped into reproduction. In that way, you don't have to worry about that. This last takeaway message is also important. So for tyrannosaurs, becoming big is not about growing longer in that sense. They don't do that. It's about growing faster, right? They've managed to accommodate faster growth. So they don't do what crocs and lizards do. Oh, you want to get really big? Well, live longer, right? Live longer and you'll get bigger. No, they're doing something very different. They are saying, no, I don't want to have to wait to get that big. I want to do it in a shorter time period. And that suggests also, again, things like being endothermic and that kind of material, or at least mostly in that way, have evolved to some degree to accommodate these animals getting bigger, being able to shunt all this energy into their growth. It doesn't mean that they're like avians, right? And this is why when we say endothermic, I wanted you to remember that endothermic does not guarantee, by and large, that these animals are sitting around and snow is landing on them and burning off, right? It's not like they're sitting in the outside and they're hot to the touch. It does mean that their bodies are warmer than the outside probably, and for most of the time. They're still slower than avians, so they're about 30 to 50% slower. Again, avians are doing things a little bit differently. And probably fast running for these large guys is out of the question as they get really, really big. So we have all sorts of interesting questions that we could ask about their ecology. Are they pack hunting? Do they even hunt? Right. So are they mostly scavenging or not? By the time they get to the adult size in that way. Actually, there is some indication that at least members that are related to tyrannosaurs may have pack hunted because we have bone beds with animals of differing ages, and so maybe juvenile animals would congregate, or at least somewhat juvenile would congregate, and then they could therefore hunt down larger animals together. Okay, so that was the other paper that I gave you, and that is also a very interesting paper and very easy to read. And this is the last one that I'm going to talk about, which is what is called the Rise of the Titans, which talks about how do you get to be sauropods. Now, we have talked a bit about being a sauropod. We've certainly talked about sauropod growth now, but one of the things that we would like to be able to do is explain why did sauropods get so big, but we don't have other gland groups get that large. We really don't see that in other locations. It hasn't evolved since, and it didn't evolve before. And we're back. Sauropods appeared, the original thinking was sauropods appeared to grow large because they evolved sort of radically new adaptations to that growth. They accommodated these new adaptations that were really different. They did something very different than everybody else. Well, that is probably not true. We think now that sauropods are what we call pre-adapted. They had adaptations that allowed them to get large, not that they acquired these adaptations that allowed in that way and acquired them as they were getting large. They had them prior to that and then used them for those reasons. So we are, in this case, we're going to go through some of these pre-adaptations that allowed sauropods to really get enormous. And that you will, I think, when we are done with this, be comfortable in saying it is unlikely that mammals will ever attain sizes nearly as large as a sauropod. Given an infinite amount of time, mammals just don't have the pre-adaptations that would allow them to do that. So this is an example of an animal that is, again, this animal sits very, very low on the tree, right? We've looked at very, very primitive animals relative to the sauropods. This one up here, I don't know why this one is, but it has little broken knees, and it can't extend its legs. This author has forced almost a quadrupedal-like look to it. But keep in mind, if the animal doesn't hold its knee up to its body like that when it's walking, these arms would be much further away from the ground, right? And it would look very much like a theropod, which they are very closely related to in that way. So what makes an animal like this, right? We know they start as these small theropod-like animals. How do we get an animal like this to an animal the size of a building, right? That weighs as much as multiple bus loads of people. Right? How do we do that? Well, one of the things that's really nice for sauropods is they evolved from an ancestor that became herbivorous. And if you really want to get big on land anyway, you don't want to be carnivorous in that way. It's very difficult to find enough food as you get bigger and bigger and bigger. Now, this is not actually entirely true if you're in aquatic systems, right? The largest mammals are in fact whales, and they are carnivorous. But in terrestrial systems, the food chains are shorter, and you need access to plant material. It's very difficult to imagine you getting enough chickens, let's say, to get to become the size of a stadium, right? Think about how many chickens you would have to eat, and also how fast you would have to hunt down chickens to get them. Whereas if you want to get to the size of a stadium, but you need to find plants, you can find plants. You need to eat a lot of them, but you can find them, and they are there. Some other pre-adaptations, of course, that we know about, these pneumatic bones and this one-way breathing are really important to probably archosaurs, and the evolution of that within the sauropods is probably relatively important as well. Pneumatic bones, of course, lighten the load, right, so they don't have to carry big, heavy, dense bones around with them like you do. Right? That is a problem for you if you're trying to get truly enormous. And it also, especially for sauropods, it allows them to remove weight from the neck very easily. Right? If they can evolve larger and larger pneumatic bones, they aren't accommodating larger and larger amounts of bone in the actual neck. In fact, the amount of bone in the neck doesn't increase that fast relative to the length of the neck, right? Because they can keep them hollow. They can also do things like add much more efficient breathing. They have a much more efficient breathing system, and for animals that have necks that are longer, right, than multiple buses or a bus, you need to be able to be very efficient in your breathing because it takes a long time to get you air down into your lungs and then back out again in that way. So you want a relatively efficient breathing system for that. And so those two pre-adaptations, sauropods did not sit down at the table one day and say, well, we're going to need pneumatic bones, so we should evolve that. And while we're working on that, we should definitely get a one-way breathing. No, those were brought to the table irregardless of whether sauropods had ever evolved or not. But they functioned very effectively in providing those animals the opportunity to get large. The other thing that sauropods have that's really, really nice is this comfort with the transition from a biped to a quadruped, right? So we go from being a bipedal animal, but we transition to a quadruped relatively easily. The inverse is not necessarily the case. If you go from a quadruped, it's easy to transition to a biped. Humans can demonstrate that very clearly, partially because of things you can demonstrate that with back problems, right? Humans have a lot of back problems, and that's because the body frame of a quadruped is not well suited to being a biped, and we suffer the consequences of that as a result. They also do things like take advantage of faster growth, so these animals becoming more and more what we think of as endothermic. There are some advantages to that, but again, sauropods did not sit down and think, oh, well, if I get endothermia, I can become very large. Endothermia is evolving, and as that's evolving, it's providing an opportunity to grow a furnace, right? You can think of this thing, and the hotter you can get that furnace, the faster you can produce energy from it, and in the same way, we can get really big, warm guts. We can grow really fast because we can digest a lot of material very rapidly relative to what we had before. They also do something else that's really important, which is they never evolve chewing, which turns out to be critical for sauropods. What is the problem with chewing?
Takes up a lot of energy.
Takes up energy, and what's the other important thing?
Takes up too much space in your head.
It's not the space that's a concern.
It's time chewing.
It's time chewing. It takes a lot of time to chew. So if you, for instance, if you just want to eat a diet of nothing but pills, you will find it very easy to do that. You can sit down and have dinner in a matter of a few seconds. If you are instead interested in eating a dinner and enjoying it, well, it takes a fairly long time, and that's even if you don't sit down and talk to someone. 15 to 20 minutes to sit down and chew through a plate of food is a long time. Think about how much food is on that plate. Not very much. And how much power does that give you? Well, a plate of food provides you maintenance for, if you're eating 3 a day, for about a third of the day, right? You can imagine roughly something like that in that way. And so if you're spending a good period of time actually going through and consuming that, that's fairly time consuming. So the ornithischians that evolved this chewing, great on them, and they're impressive in their own right, but they are unlikely to ever attain truly massive sizes because chewing, as you get larger and larger, will take more and more and more time because you need more and more energy, and it's physically going to take more and more time to go through that material, right? And plants, of course, are very happy to have you chew because it costs you something, and it slows down the consumption of the plant in that way. So chewing is a great defense mechanism. A plant can make you chew a lot more. That works very well at deterring you from eating more of it. If it takes you an hour to chew through one plant, that means you're not eating a second plant. And so that is very nice for that plant. And that's especially nice when you're trying to prevent animals when you can't run away from them, right? So if you're a plant and you can't run away from an animal, making them sit there and spend more time is nice. This additional element, therefore, is really important. So again, sauropods don't evolve chewing, and that pre-adapts them to becoming enormous because they don't ever have to spend the time working with material in their mouth, and so they can remove all of that function, which is the breakdown of plant material, into the gut, and they can spend time specializing the gut to become a place where you'll have crushing and breaking and bruising of material. You'll probably have bacterial fermentation, extraction of those resources, removal of water, and then excretion, right? And so that can be done elsewhere, and you can just pull in plant material. So as long as you can build more space into the gut, you can pull in plant material as fast as you can build the space up, and that means you can make bigger and bigger and bigger and bigger sauropods because you're not concerned. Every time you make it bigger, you get more gut room. Every time you make that bigger, you get more gut room. Every time you make that bigger, you get more gut room. And every time you're doing that, you're still having a very functional cropping beak, which is just pulling plant material into that gut and filling that gut up as fast as you can build up the volume. Do you have a question? Okay. These guys are also very good at becoming quadrupeds, which is another element of them becoming these large sauropods. And they eventually become these enormous animals, right? But they start off relatively moderate in size. This is an animal that is sitting now squarely on the bounds between what we think of as our classic huge sauropod and our very small, what people would look at and say, oh, that's like a little raptor thing. Yeah, but it's not. It's a sauropod. I mean, it looks kind of similar, but it's not. So how do they get big? Well, they win the lottery. They win this evolutionary lottery. They have all these pre-adaptations which they had no control over, right? Sauropods did not 100 million years before get to decide, oh, diapsids would be really nice if they evolved. They started on their way to evolving unidirectional breeding. That'd be really good for us. They have no control. And they also apparently are a group that had numerous adaptations that happened to align. So you can imagine all these different points happening to align at the same time and pointing in the same direction, and that provided a pathway which these guys could run down. And this allowed this evolution of this huge size. Not that sauropods were going along systematically picking up, well, that's a good adaptation, so now we evolved that. Well, that's a good adaptation, so now we evolved that. Not in a dissimilar way from the way that we evolved limbs, right? It wasn't efficient for quadrupeds necessarily to evolve in, or early lobe-finned or early fishes, but it functioned very well in an aquatic environment to help push the animal up off the ground and provide support for the body in that way. It would be very difficult to imagine a fish only had two fins, how you would get animals on the land, right? It would be like worms with legs in the front, just sort of scooching along on the ground. And therefore, there is likely no other group that currently that has any of these adaptations that would allow it to evolve. So if you gave birds more time, birds are unlikely to evolve this. They don't have some of those adaptations, right? They may pick them up, but they've lost certain things that would make them good at this. And so this group is unique, and it will probably remain unique in that sense that large size is rare, and these guys were really special in the way that they got to it. Okay, so that covers the growth lecture. Now, we are short on time, or we are shorter than normal. So again, what I'm going to do is I'm going to transition to this next lecture, which is going to deal with ecology and primarily feeding of animals, and that's so we can keep moving through the lecture material.